Next one. 24 question, 24, 2024 question. Right? 24. Right, okay. No questions, right? Right, no questions, no? Right, we'll move on. 24. A thin heating element made from a conductive material of resistivity rho has a shape of a rectangular strip with a length L, width L and thickness T, as shown in figure 1. First one. Write down an expression for the resistance R of heating element in terms of rho L WT. Right. So we know R equals rho L over A. Then rho L over area. Area, perpendicular area can be written as TW. Then rho L over TW. Right? Rho L over TW. Next. Then if L equals, okay, so calculate the resistance of the heating element. Okay. Then R equals, plug these values, rho is 8 times 10 to the power minus 5. Length is 100 millimeters 10 to the power minus 3 over W 20 T 5 micrometers. Then 5 micro 10 to the power minus 6 and W 20 milli 10 to the power minus 3. Right, then 10 to the power minus 3 to 10 to the power minus 3 cancels 20 times 5, right, and 5 also cancels. Then 80, right, 80 ohms, exactly 80. It cancels and 80 ohms. 80 ohms, right. Then part B. Part B. As shown in the figure 2, a wearable heating pad is designed for localized heat therapy. Right. Using the above thin heating elements, the heating elements are arranged as shown in the figure, along with a 40 ohm standard resistor. The pad is connected to a 24 volts DC, DC source with a negligible internal resistance. Thin heating elements are represented by rectangles. Okay. Then the heating pad should produce at least 7 watts to deliver the required required therapeutic heat. Required therapeutic heat. Okay. First one. Calculate the resistance of branch AF and branch BE of the resistance of AF, right? Okay. Now one such resistor was 80, no? Then RAF is they are in series combination 80 plus 80 plus 80. Then 240 ohms. Then we need RBE. RBE is 80 plus 80 plus 40. That is 200 ohms. Right? Part 2. Part 2. Calculate the current through the branch BE. Current through BE. Okay. If this is 24, right? If this is 24, these points are same, no? Since these points are same, see? Since these points are same, right? Potential difference across BE is also 24. Potential difference across BE is also 24, right? Then for that branch, apply V equals IR. Then delta V equals IR. This is for BE. Then this is BE, right? Delta V BE is 24. And I need current. Calculate the current through BE. Okay, we need the current I. R is 200. R is 200. Then 2 and 24 cancels, no? 12. Then 12 over 100. 12 over 100. 12 over 100 is 0.12 amperes. 0.12 amperes. Right? 0.12 amperes. Next, calculate the power dissipated in the branch BE. Power dissipated in the branch BE and the entire circuit. Does the heating pad produce the required power? Okay. Third, calculate the power dissipated in the branch BE. Okay. Then since current is known, we know power is given by I squared R. Then power of branch BE is, right, I squared is 0.12 squared. So we can write it as 12 times 10 to the power minus 2 squared, and R is 200. 12 squared is 144. Then 10 to the power minus 4 into 200. Right? Then uh, these two cancels. 288 means 2.88, no? 2.88 watts. Right? 2.88 watts. Then since resistances of AF and CD are same, their powers are same, no? We can find their powers also. Then power of AF equals power of CD, because their potential differences are their resistances are equal and currents are also equal. Right? Currents are also equal. Right? Since current is not found, we'll go with the potential. Potential is known. No? We know we can write this as V squared dou R also. Power, we can write it as V squared dou R also. Now V is 24. Then 24 times 24 over resistance was 240. Then 24 times 10. That is 2.4 watts. That is 2.4 watts. PAF and PCD both equals to 2.4 watts. Then total power can be written as, right? Then P total. Then P total is power of AF branch plus power of BE branch plus power of CD branch. No? Then AF is 2.4. BE was 2.88. And this is also 2.4. Right? Then 2.4, 2.4, 4.8. Then 4.8, 6.8. That is 7.68, right? Then 7.68 watts. Right. Now it's asking whether it can produce the required power. Required power was 7, right? Required power was 7. Then write to your final answer. Yes, it can, since 7.68 watts is greater than 7 watts. Since 7.68 watts is greater than 7 watts. Right? Part 4. Part 4. Calculate the total power dissipation of the circuit if the thickness of all the heating elements is halved. Okay. If the thickness is halved, resistance becomes see, now what was the equation we proved? Right, we thickness equation R equals where is it? R equals rho L over dW. See, R equals rho L over TW. Now thickness is going to be halved. If thickness is halved, resistance is doubled. Right? If thickness is halved, resistance is doubled. Then the question is total power dissipation. Okay, if this is halved, then we have to find the new power. Then new resistance of BE. New resistance of BE is, say, RBE dash. Now, if resistance is doubled, 1 becomes 160 now. Right? 80 becomes 160. Then BE 160 plus 160, 160 plus 160 plus 40. That is 360 ohms. No? That is 360 ohms. Right? 360 ohms. Then new power here is power of BE, new value, say dash. Right? Say dash. Now still potential difference is unchanged. Then we'll go with the potential difference, V squared over R. Then 24 times 24 over 360. 24 times 24 over 360. Right? Then 12 times 2, 12 times 30. 6 times 4, 6 times 5. Then it becomes 1.6, right? Then this is 1.6 watts. 1.6 watts. Right? 1.6 watts. And for other two, when resistance is doubled, right? When resistance is doubled, now new resistance of AF is, right? That is, previously it was 240, no? Now it is doubled. Then it becomes 480 ohms, right? Then powers are, so since potentials are, resistances are equal, power of AF equals power of CD, right? V squared dou R, then 24 times 24, right? Over 480 now, over 480 now. Then 24, this is 20, then by 4, 6, and 5, then 1.2, no? 1.2 watts, 1.2 watts, right? Then new power is the V new, right? Uh, new power of AB plus new power of BE, right? AB name AF, new power of BE plus new power of CD. Then AB is 1.2 and PE was 1.6, right? 1.6 plus this is also 1.2. Then 1.2, 1.2, 2.4, then 4, right? 4 watts. New power of the system is 4 watts now. New power of the system becomes 4 watts. New power of the system becomes 4 watts now. Right. Then fifth one. If the length L is equal to the width W, show that the resistance is independent of the surface area LW of the heating element shown in figure. Okay, then resistance is, right, it goes rho L over TW. Now it says if the length is equal to W, if the length is equal to W, then rho L over, we can write this as TL. If length and these two equal, then it becomes rho over T. Right, that's a simple showing, rho over T. Right, this is independent of LW, independent of LW, right? Then right, so that okay, we have shown 6. Calculate the resistance per unit square of the top surface of the above heating element having thickness 5 micrometers. Okay, then R equals rho over T, no? Rho was given before, 8 times 10 to the minus 5. Our thickness now is 5 micrometers 10 to the minus 6. Then 16, right? 16 ohms. 16 ohms. Right? That part is done. Part C. Part C. Assume that a heating pad contains resistive elements made of two thin layers deposited on top of each other. Layer 1 made of a material with resistivity that remains constant with temperature. Right. Then something like this. Right? Layer 1 and layer 2. Right? Layer 2 made of a material with same resistivity as layer 1 initially, but resistivity increases as temperature increases. Okay. The heating pad operates using a constant voltage source. Giving reasons explain what will happen to the power dissipation of the modified heating pad over time. Okay. Check these two separately. What happens? Check these two separately. Resistance of layer 1 remains unchanged. Resistance of layer 1 remains unchanged, right? Then resistance of layer 2. Now with the time what happens is temperature increases, right? So with the time, over time, the impact is with the time temperature increases. When temperature increases, resistance increases. Then resistance of layer 2 increases over time, right? Resistance of layer 2, we asked about resistance of power dissipation. Power dissipation. Okay, then we can write about power at once. Then power on the resistance, power. Right, so we know about power dissipation, right? Power. Then about power, that is opposite of the resistance, no? Right? Power you can't know, no? Because we know our equation is, right, about power. Power is given by, if potential difference is unchanged, V squared dou R. Right? Potential difference is unchanged, V squared dou R. Then when R increases, power decreases. Then power of layer 2 decreases with time, decreases with time, decreases with time, right? And about total power also asked, right? Therefore, right? Therefore, total power. Now, total power is the addition of these two, no? Now, one decreases. Therefore, total power decreases with time. Total power decreases with time, right? A small explanation, right? You have to explain, right? Part D. A DC source to supply power to circuits can be constructed using a suitable step-down transformer here. A transformer is used to step down the input AC voltage of 240 RMS, 240 RMS to an adjustable output AC voltage between 12 volts. Between 12 volts and 48 volts. Okay, between 12 volts and 48 volts. The transformer has 800 primary windings. At the output stage, the transformer output is converted to a DC voltage. Right, first one. Now it is connected to transformers, right? Transformers are initially coming from magnetic induction, right? Electromagnetic induction. Now this is connected to a transformer. Write down an expression for the ratio of primary voltage to secondary voltage of the transformer in terms of the number of windings in primary and the secondary. Okay, so that's a known equation of Vp over Vs equals Np over Ns, right? Np over Ns. Equation of a transformer. Second one, if the RMS voltage of the secondary coil can be varied between 12 volts and 48 volts, calculate the range of number of windings required for the coil. Okay, then for 12 volts, first, if we find for 12 volts, then Vp over Vs, primary coil is 240, right? Primary coil is 240. Then 240 over 12 equals primary windings 800 over Np, right? Then simplify 0 to 0 cancels, 8 times 3 here, 8 times 10 here, then 3 times 4 here, then Np equals 40, right? 40 windings, 40 turns, 40 windings. Then for 48 volts, 240 over 48 equals 800 over Np again, right? Then 0 to 0 cancels, 8 times 3, 8 times 10. Then 3 times 16 here. Then in that case, Np equals 160. Then the range is asked, right? So therefore, the range of windings is, right, 40 to 160. Right, the range is 40 to 160. Range is 40 to 160. 40 to 160. Right. Part 3. The DC output voltage is 80% of the RMS output voltage of the transformer secondary coil. If the desired fully rectified DC output voltage is 24 volts, calculate the output RMS voltage of the transformer. Right, then finally we need 24. 24 is only 80% of the RMS, no? Then V equals, right? V equals VRMS times 80%. 80% of this VRMS is here, right? Then VRMS is 24, right? VRMS is 24, no? VRMS is, sorry, V is the 24. For the output voltage, 24, ne? Yeah. Then this is 24. Then this is 24. VDC is 24. VDC is 24. I need VRMS now, right? This is 0.8, no? 0.8. then Vrms equals 24 over 0.8 means 8 over 10, then like this 8 over 10. 8 times 3, then it becomes 30 volts. It becomes 30 volts. Right now, 80% is utilized, then RMS value needs it is 30 volts. Right? 4. That's the last, right? Yeah. Question 4. Question 4. The transformer supplies power to a load that consumes 120 watts at 24 DC. 24 DC. If the power loss due to joule heating in the secondary is 10%, okay, there's a heat loss now, there's a power loss of the power consumed by the load, calculate the RMS output current of the transformer, right? RMS output current. Then we know power is I know, then VRMS, IRMS, right? Power is VRMS, IRMS, right? And the total power is 120 watts, but there's a heat loss or power loss of 10%. Then total power consumed is 120. 10% loss means, right, 110%, right? 10% is lost. Then total power consumed here is 110. Then VRMS was 30. That we know, right? We need IRMS. Then this is 30 times 4, no? 30 times 4. 0 to 0 cancels off. Then IRMS equals 44 over 10. That is 4.4 amperes. 4.4 amperes. Right? 4.4 amperes. Right. The last part is a little bit a creative part. Last part is a bit creative part. Right? A bit creative part, and that's a good part. 24 question.